Hello everyone, welcome to this new lecture on statistical physics. Today we're going to continue our discussion of Bose Einstein condensates in the ideal Bose gas. And we're going to recap very quickly what we said in the last lecture. We saw that according to the density of states integral approximation, one cannot lower the temperature of a Bose gas at fixed density below a certain critical temperature. And we saw that to resolve this problem, this inconsistency, we had to notice that the integral approximation does not take into account contributions due to the ground state because we assumed it had zero energy. But when we put back in the contribution due to the ground state, the result is that we got this nice plot for the ratio of excited states and the ratio of ground state, the ratio of excited particles and the ratio of the ground state particles. We saw that below the critical temperature, the ratio of excited particles started to decrease while the ratio of ground state particles started to increase. And this was due to the fact that below the critical temperature, any particles that were added to the system went directly to the ground state. Okay, so the goal of this lecture is to essentially to calculate the thermodynamic quantities, the important thermodynamic quantities, using the correct approach of including the contribution to the ground due to the ground state. Okay, so we begin with pressure. So recall that pressure is given by in the grand canonical ensemble, pressure, or better, pressure is equal to minus the grand canonical potential over the volume, or in other words, 1 over beta log of the grand canonical partition function over the volume. Okay. Next, what we have to calculate this log of z, and log of z. Well, we're going to do the integral approximation. So we're going to do the density of states times log of z dE from 0 to infinity. This is going to take care of the excited states, but to take into account the ground state, we're also going to have to include the contribution due to the ground state, which is this, right? Recall that this is the expression for the density of states. At this point, it's essentially imprinted in your mind. It should be, after having repeated it so many times. I'm going to get a minus because we're going to write it as 1 minus z e to the minus beta e dE minus log of 1 minus z. Right, now this can be integrated by parts, and what you're going to find is the boundary terms are going to vanish because the 0 is going to vanish due to the e, while the infinity term is going to vanish due to the 1 over 1 minus z to the e minus beta e term. So that's going to happen, and the end result is that we only get the integral, right, which is going to come with a minus sign, which cancels out with this minus sign. So you get v over 4 pi squared 2m over h bar squared 3/2 2/3. I'm going to write it directly as this, which will be understandable in a second. So x to the 3/2 over z to the minus 1 e to the x minus 1 dx. Okay, so I wrote it directly as a Bose Einstein function because it's recognizable. This is g of 5/2 z times gamma of 5/2, right? And so the end result is that you get 1 v over lambda cubed times g of 5/2 z minus log of 1 minus z. And so if we divide everything by v and beta, we get the pressure. So the pressure is going to be equal to kBt over lambda cubed g of 5/2 z minus kBt over v log of 1 minus z. Now notice, obviously, if we're below the critical temperature, so if if we're above the critical temperature, so if T is greater than Tc, then Z is less than 1. So log of 1 minus Z is finite. And as a result, this finite number divided by the volume, which is infinite in the thermodynamic limit, is going to vanish. Okay? So P is going to be equal to kBt over lambda cubed times G 5/2 of Z. If instead T is less than Tc, right, then Z is equal to 1, that's true. But remember the scaling of Z. Z is, but Z scales as 1 over n, right? And as a result, you're going to get log of 1 over n, 1 over n plus 1. That's right. Yeah. And so this is going to be log of n over volume. Now n goes to infinity, but this goes to infinity faster, so this whole thing is going to approach 0, and so again, this second term is going to be negligible. So again, P will be equal to kBt over lambda cubed g of 5/2 z. So we see that in either case, this log is going to either be too small or diverge too slowly to give a non-zero contribution. And so the pressure is just going to be given by the excited states, which makes sense because ground state has no net energy, has no net momentum, so it can't possibly contribute to the pressure of the gas. Okay, so I'm just going to square this part. Okay, great. So we found the pressure. Note, interestingly, that because below the critical temperature Z is equal to 1, right? This is essentially a result of the fact that below the critical temperature, only the ground states start to get occupied. So your chemical potential has to be 0, and hence Z is equal to 1. So at the critical temperature, pressure at Tc, well, that's going to be equal to Kb Tc over lambda cubed g 5/2 of 1, but that's Kb Tc over lambda cubed, or critical lambda cubed, of zeta of 5/2, right? And even if we're below the critical temperature, Z is still going to be equal to 1, and so we're still going to find kBt over lambda cubed zeta of 5/2. So the behavior of the pressure is going to be that of T temperature to the 5/2. Good. Next, another interesting thing to look at is the internal energy. Okay, so let's add a new page. So the internal energy is given by minus derivative with respect to beta of the log of Z, and this is done at constant fugacity, so at constant Z. And so this is equal to, again, we're going to do the we're going to use integral approximation. So it's going to be equal to v over derivative with respect to beta minus derivative with respect to beta of v over lambda cubed g 5/2 of z. Now, we should add the contribution due to the ground state, right? So this is going to be the energy U of excited states plus U of GS, but the ground state has no energy, so this can't possibly be non-zero. Okay, so this is fairly easy to calculate. I won't do it because I forgot what lambda, well, we could do it actually. So set lambda equal to alpha t to the minus 1/2, and this is equal to minus v g 5/2 of z. Remember, z is constant. The derivative is done with z constant. Derivative with respect to beta. Wait, actually, simplify matters. Let's use beta rather than t. Right? So derivative with respect to beta of beta to the minus 1/2, but this is just alpha v g 5/2 z over beta to the 3/2, and when you recombine alpha and beta here, the result is that you get minus 3/2. That's it. So we're actually going to get a 3/2 here, and so this is going to actually be 5/2. Right, and when we combine alpha with beta to the 5/2, we get 3/2 v kbt over lambda cubed g of 5/2 z. So there you go. This is internal energy. This holds for all temperatures, for all T's, right? And it's because we did include the ground state contribution. It just turned out to be vanishing, just like with the pressure. And note that this is also equal to 3/2 PV, right? So this is actually the equation of state, which is quite nice. Great. One final quantity that we should take a look at is the heat capacity. So what is the heat capacity? Well, it's given by the derivative of the internal energy with respect to temperature at constant V. Okay, so we're looking at the constant volume heat capacity. Now, this is no longer done on constant fugacity. So what this means is we're going to get one derivative due to the temperature, one due to the explicit dependence on temperature, and then one derivative due to the implicit dependence on temperature, because this z here is going to depend on t. Right? Remember, z is equal to... Okay, so I just realized I stopped recording the audio, so I kept writing without recording what I was saying. So I'll run through the calculation, which I've done for the past 10 minutes. So I think I was saying what the fugacity looked like. Okay, so the fugacity is equal to 1 below the critical temperature, right? And it's going to be equal to the solution to this equation right here, which we derived in the last lecture, above the critical temperature. Why is this? Well, it's because, above the critical temperature, we know that this holds exactly in the thermodynamic limit. So the solution is obviously going to give us Z. Instead, if we're below the critical temperature, any particles we add are going to go directly to the ground state. So the chemical potential has to be equal to 0. And if the chemical potential is equal to 0, then Z is equal to 1. Or another way to look at it is, below the critical temperature, the number of excited states is fixed. It's going to remain fixed at the critical density, the critical number of particles in the excited states. And so for that to remain fixed, you need Z to be fixed to 1. Okay, so this is the behavior of the fugacity. And note that there's a temperature dependence, right? This is what I was getting at. Because there's a temperature dependence, our derivative right here is going to have two contributions. One contribution is going to come from just explicit temperature dependence right here, this T over lambda cubed. And if you calculate the derivative, well, T over lambda cubed is equal to T to the minus T to the 5 halves. And so you're going to get a 5 halves T to the 3 halves. And it's just going to give you 15/4 kBV over lambda cubed times G 5 halves of Z. But then we're going to get another contribution, which is going to be due to the implicit dependence on temperature in here. Z depends on T, and so using the chain rule, we're going to get 3 halves, blah, 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 dz dt times d dz of G of 5 halves Z. Okay? So our goal right now is to calculate these two partial derivatives. Okay? This and this need to calculate. Okay, and luckily enough, they can be calculated exactly. The first one is, or the second one is very easy to see. Let's consider the general case of Gn of Z, right? We can write it as this sum right here, right? This is the sum representation. And when we take the derivative, it's going to be equal to m z to the m minus 1. This m is going to cancel out with m to the n. And we're going to write it as 1 over z times z to the m. Okay, so it's going to be equal to 1 over z sum of z to the m over m to the n minus 1. And this is just 1 over z times the n minus 1th Bose Einstein function. Okay, so this is very trivial to see. What is a bit less trivial is this first derivative right here, dz dt. The way we do it is we're going to use this expression right here for the particle density. I'm going to differentiate it with respect to temperature, right? So differentiate both sides with respect to temperature. The left-hand side is just going to give you minus 3 halves n over v lambda cubed over t. While the right-hand side is going to give you, again using the chain rule and this property right here, which we just calculated, it's going to give you dz dt times 1 over z g of g1 halves of z. Flip everything, isolate the partial derivative, and you find that partial z partial t is equal to minus 3 halves z over 2t, right? N over v lambda cubed times 1 over g of 1 half z. And again, we can substitute, instead of writing n over v, we can write g 3 halves over lambda cubed. And when we do that, you just get this expression right here, minus 3z over 2t, g 3 halves over g 1 halves. Note, however, that in this derivation, I used this expression, which only holds above the critical temperature. So this derivative is only true above the critical temperature. Okay, this one holds in any temperature regime, but this one only above the critical temperature. We're going to work out the below critical temperature later. Okay, but if we're satisfied with working above the critical temperature, we see that CV is equal to 15/4 kBV over lambda cubed G 5 halves. We evaluated that earlier. And then plus 3 halves kBV over lambda cubed T times dz dt, which is this, times 1 over z g 3 halves. This was the derivative of the g 5 halves function. Simplify things and we find 15/4 kBV over lambda cubed g 5 halves of z, again, minus 9/4 kBV over lambda cubed g 3 halves squared over g 1 half. Okay, the z's and the t's cancel out. Finally, because we're above the critical temperature, we can use this expression, substitute it here and here, and write CV as 3n kb over 4 times 5 g5 halves over g3 halves minus 3 g3 halves over g1 halves. And this holds, again, above the critical temperature. Okay, this is a nice expression. If we're below the critical temperature, well, Z is just equal to 1. No temperature dependence. We don't care about what temperature we're at. So this is going to vanish, right? This is going to vanish to 0, and we're just going to end up with this first term. And so we're going to end up just with the first term, 15/4 kb over lambda cubed g5 halves of, and Z is equal to 1, right? So we got 15/4 kb over lambda cubed times the zeta function of 5 halves. Wonderful. So we found this specific heat capacity, right, which is actually just the heat capacity over the volume, okay? That's how the V's here cancelled out. And let's look at a couple limiting cases. So first of all, the most interesting limiting case is the high temperature case, right? So as T goes to infinity, it's quite useful to know this. The limit as Z goes to 0, well, first of all, T goes to infinity means Z goes to 0, right? And then the limit as Z goes to 0 of the ratio of any Bose Einstein function with positive n and m is just 1. And that's fairly easy to see because these are just, right, polynomials, and so you're just going to get the ratio of the dominating ones, and that's just 1. And so as a result, this is going to give 1, this is going to give 1, so we get 5 minus 3 inside these parentheses, and that's just 2. So CV is going to be equal to 3n kb over 2. Okay? This is actually the same as the ideal gas specific heat. And so what this tells us is that a high temperature Bose Einstein gas behaves as a high temperature ideal gas. Great, let's actually plot this, the specific heat capacity. I'll try to do it by hand. Almost straight. There we go. So here we have the CV. Here we have the temperature. Let's say the critical temperature is here, more to the left perhaps. Here. Now we know that we're going to have an asymptote at 3/2 n kb. So we know that as t goes to infinity, it's going to approach this value asymptotically. So it's going to do something like this. Instead, below the critical temperature, it's actually going to have, if you plot it, a behavior that looks like this. And here, we're going to have a kink. So it's not going to be its derivative. It's not going to be continuous anymore. And that's very important. That's a very important fact. So this right here, kink. Okay. Now this is actually a sign of something called a second order phase transition. Okay. Why? Well, because remember, CV is the first derivative of u with respect to temperature at constant V. So Cv, the derivative of Cv with respect to temperature is going to be equal to the second derivative of U with respect to temperature, right? And this is discontinuous, right? Discontinuous because we have a kink right here. It's going to be discontinuous at the critical temperature, and hence the second derivative of the internal energy, which is a thermodynamic potential, is going to be discontinuous. And whenever the second derivative of a thermodynamic potential is discontinuous, we say that we have a second order phase transition. So there we go. We have our very first example of a phase transition, a quantum phase transition. Note that this only holds because we're working in the thermodynamic limit, right? If V and N were finite, you would actually be able to zoom in into this kink, and eventually it's going to smoothen out and give a smooth curve. And so this discontinuity would not be there anymore. So this phase transition and all phase transitions in general can only occur when you're at infinite particle number and infinite volume. And yeah, so that's it. This was our discussion of Bose Einstein condensation. And we're going to look at more phase transitions later, especially looking at the Ising model, the Potts model. And yeah,